Perfect. So today we will have Dr. Fei Lu, who is an assistant professor in the Department of Electrical and Computer Engineering at Drexel University. He received the Bachelor of Science and Masters of Science degree from Harbin Institute of Technology in China in 2010 and 2012, respectively. And he received a PhD from the University of Michigan, Ann Arbor in 2017, all in electrical engineering. Previously, he was a postdoctoral research associate in San Diego State University from 2017 to 2018. His research focuses on high efficiency power electronics technology, leveraging the next generation of wide bandgap semiconductor devices, especially for electric vehicle wireless charging and solid state circuit breaker applications. His research has received 3 Best Journal Paper Awards from the IEEE Transactions on Power Electronics and 2 additional conference awards. Thank you so much for joining us, Dr. Fei Lu. We're really excited to have you.
Thank you. Thank you very much for the introduction. Please first allow me to share my screen here. Okay, I believe everyone can see my screen, right?
Yes.
Okay, good, thank you. Let me full screen here. Okay, let's start. Let me. Okay. Thank you, everyone. Thank you for the introduction and also the invitation from Professor Bai. It's my pleasure to be here and present my recent research achievements in the solid-state circuit breaker. And I know UTK team also have a project ongoing with DOE, and I hope we can have a lot of discussions and also future collaborations in the future on this topic. Thank you. And let's first start the technical part today. First, I want to start from the introduction about the electric DC power systems. And we all know that electric DC power system is very important. It has been widely used in a lot of applications, such as the generation, especially the renewable energy, and also the distribution lines, the protective devices, the power converters, and also the energy storage unit, also the DC to AC conversion. So specifically on the electric vehicle charging applications. So considering all of these different systems, so we need to further study the electric DC systems. And specifically, people also talking about the new concept, like the DC system for residential buildings, the networked DC microgrid systems, and also the hybrid AC-DC system, because traditionally we have the AC system already there. We need to connect the newly established DC system and have the good combination between them. And the other thing we want to do a compare between the traditional AC system and the DC systems. So usually we can see that the DC system has higher efficiency at the same voltage level. And also it does not need the frequency synchronization. So which means the control is is much easier. And also it does not need the reactive power compensation. So which is also a painful part in the AC systems. And is easy to be integrated with the renewable energies, especially the solar energy system. And also since there are a lot of DC load in our real life, and then if we use the DC system to supply power, we can expect that there will be less energy conversion stages. So since there are a lot of advantages in the DC system, and we also need to look at the DC system developing driving forces and the potential limitations. For example, here we can see a lot of driving forces from the integration of DGs distributed generators, the growth of DC load, supply power to remote areas, the interaction between the AC systems, the high stability provided by the DC systems, the saving of the power and the lower cost. All of this has different interference with the final application of the DC systems. And there are already references, research papers talking about the evaluation of different factors. And we cannot also ignore the influence from the market side. The market has a lot of demand and requirement for the DC systems. For example, there's commercial buildings, EV charging applications, communication centers and data centers, and also renewable energy. All of this has the real demand from the market, and they are helping to promote the development of DC systems. So considering all of this, we also need to see the technical barriers or limitations in the DC systems, because we know this is a new technology. It has not been well developed. For example, we can see there are limitations from the DC circuit breaker side, from the low thermal capability of the semiconductor devices, because in the traditional AC system, usually transformers are widely used. For the transformers, since it's made by metal, copper, or magnetics, so the thermal capability is much more stronger and reliable than the DC systems. And also, we need to look at the different DC to DC convergence, the voltage source converter, and the multi-level modular converter technology. And also, most importantly, there's no specific standard there. Although there are a lot of talking there, but the standards is still missing for the DC system. And this establishing process is also very important. For today's talk, we will majorly focus on the DC circuit breakers, since this is also a very new research area. For the circuit breaker, we can look at its functionality. It plays a vital role in the DC system protection, because we know for any system we design to use it, but we also need to plan for the potential faults in the system. It protects the DC system from overload and short circuit faults. It can also de-energizing the part of the DC system for maintenance, because sometimes we not only need to cut off some part from the DC system because of fault, sometimes we also need maintenance, and we need to trip the specific part from the DC systems. For example, if we have a fault here, the closest circuit breaker need to react to this fault and cut this faulty area out from the entire systems. And for the DC system itself, based on the recent research, it can be classified into 3 categories: the mechanical circuit breaker, solid state circuit breaker, and the hybrid circuit breaker. The hybrid ones means it is a combination of both the mechanical and the solid state ones. For the mechanical breaker, the key part is a mechanical switch. And for the solid state, the key part is the solid state switch. Usually it's made by thyristors, IGBTs, or MOSFET. And for the hybrid one, it includes both the mechanical switch and the solid state switches. Here, I also want to show the timeline for the development of circuit breakers, especially the DC circuit breaker. And we all know that the DC electric system was established by Thomas Edison about 100 years ago. At the very beginning, people only expect to use it, and there's no specific protection devices already there to be connected in the DC system. If there is, there's some very general mechanical switch contacted by metals. And then starting from the 1940s, people start to initialize the research on DC circuit breakers. And the first commercial available high voltage DC system breaker is a mechanical one, actually. It's in 1954. And then after that, since the thyristor-based devices are well developed, then from 1970s to 80s, there are a lot of thyristor-based breaker and also mechanical breaker proposed or developed by the commercial companies. And then from about 20 years ago, later 1990s, then the circuit breaker market started to be blooming because the DC system is becoming more and more popular. And especially nowadays, you can see most of the circuit breaker that developed by in the form of hybrid circuit breaker, such as the ABB, the leading company in the market. And also a lot of applications in Europe and also in China, they also use hybrid circuit breaker in the real high voltage DC system up to 200 kilowatts or even 500 kilowatts. So from this, we can see the circuit breaker market is developing, and there's a need for us as an academic institute to look into the technology and to see how we can help this technology to be more established. Then if we look at the some of the academic work from 1980s, we can see a lot of good papers start to be published. They look at the high efficiency and high electrical rating mechanical circuit breakers. And then the solid state circuit breaker starts from the 1990s when the semiconductor devices are well developed. It can provide a very fast response time, and also since the size is small, it provide very good modularity and lifetime. Because for the mechanical switch, you can see here is based on the metal to metal contact. Then the lifetime is usually a few thousand times or 10,000 times. But for the solid state switches, we all know that since there's no mechanical contact, the lifetime could be much longer. And also simultaneously in the commercial area, ABB, they are trying, they continue to develop the high voltage hybrid circuit breakers for a lot of new applications, as I showed in the previous slides. So this is one of their picture. You could see this huge tower. Actually, this is for 500 kilowatt system. And nowadays, since the wide bandgap devices are developed, so people are looking at specifically to use the thin carbide MOSFET modules to develop, we can see it, the next generation solid state circuit breakers compared to the very initial one developed in 1990s. So here, since we want to look at the solid state circuit breaker, we also need to see what can we use and what is available in the market. So this is a review paper presented very recently in a few months by ABB. They summarized the circuit breaker, the solid state devices, and how these devices could be used in the SSCB applications. For example, this is the timeline they presented how the semiconductor devices are developing over the years. So you can see at first they have the thyristor, and then there's the GTO and IGCT. IGCT also developed by ABB. And then nowadays, people can see there are silicon carbide MOSFET. Although the leading companies like Speed, they can provide up to 10 kilowatts modules available for the trial use for their partners, but it's not very commercial available. For the commercial available device in the market right now, the majority of the device is still 1.7, 1.2 or 1.7 kilovolts zinc carbide MOSFET. And then the right side, this figure, this is also developed by ABB. They did a very complete comparison of the voltage and the current rating of the available power devices in the market. You could see this line is thyristors. From here, we can easily see that thyristor it still dominate the high power applications. So you can see they have as high as 1.8 kilovolts, 6 kiloampere thyristors, and here the voltage could be 12 kilovolts, and the current simultaneously it could be 1.5 kiloampere. So these thyristors are available in the market for different applications. Of course, it could be used for the circuit breaker application. And also in the middle is the IGBT. And we can see IGBT, it's kind of a strong device. For example, it can achieve 6.5 kilovolts, 1000 ampere. However, the capacity is still smaller than the thyristors. That's why a lot of people also use IGBTs to do the circuit breaker demos. And also IGCT, as I mentioned, is developed by ABB, and the power rating is the maximum power rating is also comparable with IGBTs. Other than that, so there are also GTOs, and what we are looking here is the zinc carbide MOSFET. Although, as I mentioned before, the zinc carbide MOSFET is becoming the solution for the next generation solid state circuit breaker because of the high efficiency and also the good thermal performance of the device. However, if we look at this in a huge market perspective, there are still a lot of work to be done to promote the application of this zinc carbide MOSFET. That's why I want to mention that if we review all the papers, I mean, even the recent papers in 2011, 2021, 2022, a lot of papers, they are still using the thyristors and IGBTs to do the circuit breaker. Although zinc carbide MOSFET modules is kind of a future trend, but up to now, compared to the existing semiconductor devices, there are a lot of work to do. So here, ABB, they also give a very simple example to give you an overview why thyristor has the advantages. For example, they compare three very similar devices, 1.2 kilovolts, zinc carbide MOSFETs, IGBT, and thyristors. You can see their continuous current are very similar, 70 ampere, 56 ampere, and 60 ampere. If we use them in the regular power converter switching mode power converter application, they are very similar. However, if we look at their power current application, which is what we look at as a DC circuit breaker application, because in the circuit breaker application, we not only look at the continuous current, but also look at the power current capability. And we can easily see that the thyristors is much higher than the MOSFET and IGBT. The other thing we need to pay attention, based on the thyristors datasheet, usually it is used for the AC system 60 Hertz. And then the power current was tested at 8.3 milliseconds. But for the MOSFET and IGBTs, especially for the IGBTs, is tested in 1 millisecond. And for MOSFET, this is tested even a smaller time. It means if we are using thyristor to do the circuit breaker and use in the short circuit protection application, and we can see the pulse current capability is much higher. That's why it still has a lot of advantages, not only from the price perspective, because if we look at the price, if we name Sarisa as one time, then IGBT is 70% higher, and the recent thin carbide device, they are 5 times larger. Even we can withstand this higher cost, but the pulse current capability of Sarisa is still super high. And then the other thing is they also compared the voltage and current capability. I think we all know this, but I still want to put it here. This is a figure also provided by ABB. They want to emphasize that the Sarisa is even from the conductive perspective, the Sarisa is also better, because if you look at the voltage and current curves, you could see even when the current increase to super high, the Sarisa's voltage drop is still much smaller. And if we compare the IGBT and the MOSFET, we all know that IGBT has better capability at high current, and at the low current, the MOSFET is better. That's why the thin carbide MOSFET right now it only look at focus on the low voltage and the low current applications. So since I mentioned that the Sarisa is right now still kind of a good solution for the SSCBs, I want to explain the one typical example for the Sarisa-based SSCBs. Usually, for this semi-controlled device, the SSCB based on this could be classified into the injection-based SSCB, Z-source SSCB, T-source SSCB, H-source SSCB. So for different ones, they have a different circuit topology configuration. But the most popular one is the second one, is the Z-source one. Here I want to explain the working principle. You could see in the normal operation mode, we have an inductor in the system, in the DC system. And then if we have a fault, we can see there's, let's say, a line-to-line fault. It means the high voltage line has a huge fault current flowing to the ground or to the negative of the line. And then this is a normal, we call it a low frequency path, because this inductor in the DC system usually is super large. It's in the millihenry range. And then for the high frequency path, it means you could see we have, usually in the DC system, we have a capacitor to support the DC bus voltage. And if we have a fault at the low side, we could see there's a discharge of this circuit and of this capacitor, and this discharge is a high frequency path. And this circuit breaker actually, it is utilizing this high frequency path to protect the circuit, and specifically it is using the discharge of this capacitor to turn off the thyristors. You could see this is a typical Z-source circuit breaker. It has two capacitors, two Cs here connected through this thyristor. Then normally the thyristor turns on, but when we have a fault, this thyristor will discharge through, this capacitor will discharge through this thyristor, and then we could see it has a negative direction current or to cancel the positive current in the DC system. If this negative current exceeds the positive current, we can see this thyristor will be turned off, and we call this process the natural current commutation. Then this, I want to emphasize that this source-based circuit breaker, it has the automatic protection function, because it does not need any detection of the fault. It does not need any control to get involved. As long as you have a fault and the fault impedance is low enough, then this capacitor will discharge and the thyristor will be automatically turned off. And based on this characteristic, a lot of Z-source-based circuit breaker has already been proposed, like the cross Z-source, you can see it's like a cross structure, the parallel one, and also the series one, based on different configuration of the topology. But for any of them, the working principle is very similar. So it is when we have a fault, this fault will automatically generate a reverse current direction flowing through the thyristor and turn off this thyristor. This has been widely used. And also, as I mentioned, thyristor has a lot of advantages in terms of high current capability, higher efficiency, and low cost. This source circuit breaker is still used in the real industry applications. And I would say that this source circuit breaker is one of our target when we want to use the MOSFET, the silicon carbide based circuit breaker to compare with this Z-source circuit breaker. This Z-source circuit breaker also has disadvantage I also want to mention, because it has this capacitor and also has this inductor. The size is really large, and also response time of this thyristor is also slow. Is usually in hundreds of microsecond or even millisecond range. So the response time is the only major disadvantage or drawbacks of this thyristor-based one. But since the thyristor device is also developing nowadays, people can also build good thyristor-based circuit breakers nowadays. And after we discuss about the traditional solution, we will also want to see the working principle of the active SSCB. So the active one is kind of very simple, or we can say the straightforward. We can say this is the active switch because this is a fully controlled switch. We can turn on and off this switch at any time we want. And in the system, we also need the MOV. It's a metal oxide varistor. So this is a kind of a device to absorb the remaining energy in the DC system, because if we turn this off, we know there's the inductor. This inductor energy has nowhere to go. We have to have some device to absorb it. We usually use MOVs in the circuit breaker, and this shows the working principle. It's also very straightforward. At the first, we have a flat current. It's a normal current, and then at this position we have a fault event. Then the current will increase. And when the current increases to some level, I see at this point, this is the threshold. After we detect this, and we will ask this solid state switch to turn off. When this turn off, we can see it will generate a reverse current or a huge current on the switch. Since we have this MOV, this MOV is used to absorb the energy and limit the peak current as peak voltage. Then you could see we have a peak voltage here. It's kind of flat waveform. And then during this process, because the current is absorbing by this MOV, and then you can see the current instead it will commutate from the switch to the MOV. This is the blue dashed line. And then after all this process, since the energy is absorbed, then the MOV current goes down, and the MOV current goes down together with the line current. And after the current goes to zero, we can see this breaking process ends. So this page shows a very simple or basic working principle of this of a circuit breaker. And here, this page shows one of our design example. It's kind of complicated. I would like to emphasize a little bit about the working principle. We have 4 modes. So the first mode is very similar. You could see there's a DC source, is a line inductor, and this is the switch. This is the load. The left part, this black component here, it is used to replace the MOVs. This is MOVs. The working principle is very similar, but based on this circuit, our advantage is that we can achieve zero current switching for these switches. The basic working principle is here. So in the second mode, let's see, we have a short circuit. If we have a short circuit, we can imagine that there's a huge current increase in this loop. And then we turn on our auxiliary circuit. This auxiliary circuit will generate a reverse current. At first, we have this additional switch to generate a current. And once the current magnitude is large enough, we turn this off. And then we can see this inductor will flow through this loop. And this loop will make sure that this reverse current exceeds the fault current. So it's the same. So the working principle is similar as we are generating a reverse current to cancel the fault current. Then if the current is higher than the fault current, you can see here this body diode will turn on. And then we have zero current switching. Then we turn this switch off. And after that, so everything ends. So these two figures also show that our circuit can turn off either the load interruption or the short circuit interruption. The load means the current is kind of flat. The short circuit means the current is increasing. This is the prototype we developed. So this is the auxiliary circuit. This is our main conduction branch. This is our DC capacitor. You can see this capacitor is used to emulate the DC source, and also we have the load. So basically, the working process is we generate a high voltage here, and the current flows through this main conduction branch to the load, form a loop. And then when we want to turn the switch off, we use our auxiliary circuit to generate a reverse current flowing in the other direction. And then once this current exceeds the fault current, and we can safely turn off these semiconductor devices. This is our test prototype. You could see we connect everything together. We have the capacitor bank to emulate the DC bus voltage up to 4 kilowatts. And then it can generate 100 amperes through this big inductor to the switch and then to the load. The load is at the back side. You cannot see it hide by this scope. And then this is our auxiliary circuit that can generate the reverse current, basically how it works. And here is one of our results. You can see here at the very beginning, we turn this on, we have very flat current, and then at this point, we generate a short circuit fault, and you can see the current keep increasing. At this point, in enlarged figure shows that the peak current is about 94 ampere. It's a little bit below our targets, but we assume that this is the same as 100 ampere. And then at this point, we turn our switch off. You could see this voltage increase, and this voltage increase to about 5.36. It's below 6 kilowatts. It's below the safe range of our the safe voltage rating of our device. And then you can see this voltage will be kept for a certain amount of time, and then it go down to 4 kilowatts, which is our DC bus voltage. And other than the switch test, we also did the other test, which is we call the steady state test, because the circuit breaker eventually it will be used to conduct a huge current for a long time. And then we generate, because in our lab we don't have 100 ampere DC source, then we first build up this DC source up to 100 ampere multiple phase paralleled. And then this is our circuit breaker. You could see we have a heatsink. We have a distributed heatsink for each module, and then connect all the modules together and use it to conduct a huge current. Here's our test about the temperature. You could see we tested 1 hour actually from 0 second to 3,600 seconds. And we also test a different current level. At first, we want to be safe. We start from 50 ampere, and then 75, and then 100. We can see the case temperature at this point as the edge of the power module, the case temperature reach 59 degrees C, which is kind of acceptable. I'm not sure if I can show this. Okay, so I do have. Okay, so it can't, I cannot show this. This is a video actually. Maybe I can show from this side. Yeah. So you can see it start from 0, and then this is 10 minutes. The temperature become higher, and then 20 minutes higher, 30 minutes. We want to make sure that it reaches the thermal steady state, and then 50 minutes up to 60 minutes. 60 minutes is the final temperature. Then the final temperature is 59. We just want to make sure that we reach the thermal steady state. And after all, we also try to measure the efficiency based on the voltage drop we measured there. We can see at the very beginning, we have higher efficiency. It's above 96.96. And since we have the heat up of the power module, and we all know that the internal resistance will increase with the temperature and with the time. You could see here, with the time goes on, our efficiency goes down a little bit, but still after 1 hour, it is stable at about 99.958. Then we assume that this is our final efficiency, and then we claim, so this solid state circuit breaker has reached a very good transient and steady state operation performance. Yeah, so that's all. So thank you for listening. At last, I also list some of the references here. So I'm here open for any questions. Feel free to ask any question if you have any.
Yeah, I have a question.
Sure.
What drives that decrease in efficiency at steady state? Is it because of like thermal, I guess, does the circuit breaker just get hot, or?
Yes, exactly. If you could see here, this is the case temperature. It increases from 25 to 59. Then we can assume that internally inside of this module, the junction temperature also increases, and then the resistance of the power module of the die also increase, and then that's why we have a efficiency drop.
Okay.
Yeah. So it's here I want to emphasize a little bit, because if we look at a lot of papers online, usually they give some efficiency test, but they didn't run this 1 hour or even longer time steady state test. And then I would say usually the efficiency you can catch from some papers, most of the paper I would say is this low temperature initial efficiency. If they run that, we can expect that there will be efficiency drop.
Okay, thank you.
Okay, no problem. Thank you.
Hi, I have a question. Well, two-part question, I guess. Have you looked into any form of like cooling equipment to help with like the temperature issues that you're having with silicon carbide? And also, have you looked into working with any GaN devices?
Oh, that's okay. Two good questions. For the first question, is you mean the cooling method for this? I would say no, because if we can see the setup here, so at the very beginning, we claim that our design does not need any, I would say, active cooling, although we can have air cooling or liquid cooling mounted onto this heat sink or cold plate. But we think that will, number one, make the system more complicated. Number two is increase the size and the weight of the system. And right now we can see this system is kind of standalone. It does not need any active cooling or additional design for the cooling part. But I do think that active cooling is necessary if we want to push this circuit breaker to work at a higher current. Right now, so the nominal current we define is 100 because at first we want to be safe. But my personal estimation is that maybe 150 or even 200 is not a problem. But if we want to push the current rating to be higher, we may have to have the active cooling. That's for the first question. The second question for the GaN devices, no, generally no. However, I want to see that this is our second version design. We use this thin carbide modules, but for our first version, we use the thin carbide discrete device, which is 1.2 kilowatts, 16 milliohm from Korea. It's about $50 for each. So we first use that one to have our initial first version design. And then since the result relatively good, and then we switch to this module-based structure. And also I want to mention that technically we can still use GaN device to do that. And also considering the GaN device has a lower resistance, the efficiency could be higher. But we need to maybe care more about the power, because as far as I know, the voltage for the GaN device, the highest one is still 650. Then the power level, the voltage level would be lower. But technically you can, yeah.
Very cool, thank you.
Thank you. Another question?
Hey, Dr. Lu. Thanks for the nice presentation. So I have two questions. The first is that why do you think that zero current turn-off is required for this SSCB? I mean, if that is not achieved, what will be the issues there?
Okay, yeah, so a very good question. Actually, this is also a question we will submit the papers and received from the reviewers. So here, as I mentioned here, we generate a reverse current and achieve ZCS. Our major claim here is it can help us to reduce the voltage or the power, we call it the power or energy shock during the turn-off. So the difference here is, let's see, if in the normal case, if all the in the load interruption case, this current is usually below the rating current of the MOSFET. It could be 100 ampere defined here, but in the line current, in the short circuit case, this line current could increase much higher. Usually it could increase up to 10 times of the nominal current. For example, here we have 100 ampere nominal current. Then the fault current could be as high as 1 kiloampere or even 2 kiloampere. In that case, the current is super high. If you turn off the current immediately or only by the semiconductor device, if there's a risk, you may damage the device. And we also did the experiment. I didn't show it here. The experiment is we also use it. You can see maybe from here, our peak current here is 100 ampere, but we also did another experiment to increase this current up to 10 times, 1 kiloampere. And at that time, we observed the power shock. I mean, in the hard switch mode, we observed a power shock on the module. It could be up to 250 kilowatt. So then we think that this power shock could damage the device or at least degrade the device. We don't want to degrade or damage our modules, but we did test for the discrete device, and I think we degrade more than 10 of them. We tried a lot of times. We don't know which time we degrade the device, but eventually I can tell you that if we don't care about the power shock and energy shock, the semiconductor device will be degraded. And in the other way, if we have the zero current switching, we can make sure that there's no power shock. And then the lifetime of the solid circuit breaker could be significantly increased.
Okay. So you mean in your test, you did observe some degradation of the device after several times of the short circuit protection of that discrete.
Yeah.
Okay. Is it like what characteristic did you see to confirm the degradation, like VTH?
Okay. That's a good question. So we did observe the degradation from a few perspectives. One is the gate resistance. Usually, if we use let's say a multiple meter to measure the two pins between gate and source, we could see a large resistance there. But after degradation, we can still use it. Interesting thing, we can still use it, but the resistance between the two terminals is only in the range of a kilo ohm range, which means it is degraded. And the other thing is the resistance between the drain and source. Between the drain and source, usually if we use the DMM to measure, it's either out of range or is in the range of hundreds of mega ohm. But then after that, this resistance is also significantly reduced. It means it does not have the voltage blocking function.
Okay.
Yeah.
Okay, thanks.
No problem.
And the second question is about just this page. I saw your continuous running current is also 100 ampere. And in this page, where you tested the short circuit test, it seems it's also around 100 ampere. Does that mean you have a similar value of the current between these two?
Yeah. So for this interruption test, in this result we tested 100. And then in the other one, in this steady state, we also tested 100. Yeah, that's the same.
Are they the same prototype or?
Oh no, not so that's a good.
Okay.
So they are not the same. So maybe I can explain a little bit more here. You can see here, I'm using capacitors here to support the interruption test. So although I only put a 100 here because this is a requirement from our sponsor. And then, but we also did 1 kilo ampere, but I didn't put it here because the paper is still in review process. This setup, the paper for this setup already been published as a electronics transaction last year, I believe, or the beginning of this year, January or February. And then for the 1 kilo ampere test has not been published. We just submitted the result, so that's why I didn't put it here. But for this continuous test, we use a different setup. You can see here we developed this 3-phase interleaved current source to supply the current here. So this also has not been published. However, we expect it will be published very soon. It's already in the second revision. That's why I put it here. Because the reason is here, because this capacitor bank cannot support the current for 1 hour. That's why we didn't use the same prototype.
Okay.
Yeah.
Thank you for the answer.
Yeah, because if you imagine, okay, so here 4 kilovolt, because the voltage here it is 4 kilovolt. 4 kilovolts, 100 ampere. If we do 1 hour continuous test, we don't have the power supply.
Okay.
That's the real reason. Yeah, if we have the power supply, we will be able to do this. Yeah. in our lab, our capability is only 30 kVA. It's not 400 kVA. It's too high.
Thank you.
Yeah, any other question? Okay, well, right on the time. So Kevin, I'm not sure if we still have a few minutes for additional question.
Maybe this is a question to all the students. Anything? I think Dr. Lu gave us a very comprehensive and detailed and impressive results. The circuit breaker, I'm also pretty new to this domain, trying to learn something from him.
Yeah, I'm also new in this area. So we have done some research in 2 years, but up to now, I'm still learning a lot of new knowledges every day from the internet, also from my students.
Because this circuit breaker somehow is different from our traditional power electronics applications, right? And meanwhile, we have to compare this circuit breaker with a mechanical circuit breaker. Yeah, it's definitely something I get involved with Dr. Wang's project, this cable project to design circuit breaker. When I jump into this domain, I found, oh, actually there are a lot of things I never thought of in the past at all.
Yeah, I agree. Yes, yeah, it's super new area, and also sometimes we also need to learn the knowledge from the system level.
Absolutely.
The power grid side.
Definitely.
Yeah. If no more questions, let me stop sharing and.
Okay. Maybe if no more question, we can stop here. And
if any further questions, feel free to send me emails.
Definitely. We thank you for one more time. Thank you for your time.
Thank you very much. Thank you.
Yeah, thank you so much. That was a great presentation.
Thank you. Bye.
Bye.
Bye.